Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Now that we've seen a variety of identities, we can start working on problems that get you thinking about which identities will help us progress in the question at hand. At this level, the goal is not to memorize more formulas. It's about choosing which identity to use and why. And there's no better way to demonstrate that than jumping straight into a problem. So let's take a look at our first problem. The first thing I notice here is that on the left side, we have a fraction minus a fraction. And the denominator for one of them is 1 minus sine x, and the other one is 1 plus sine x. So naturally, you will want to put them over a common denominator. And in this case, the common denominator would be these two things multiplied together. And that is a great denominator to have because that would be 1 minus sine squared x, which is part of our Pythagorean identity. So that gives us some confidence that that should be the correct direction for us to go in. So we start with 1 over 1 minus sine x minus 1 over 1 plus sine x. And what we're going to do is we're going to multiply our first fraction by 1 plus sine x on the top and on the bottom. So then we get 1 plus sine x over 1 minus sine x times 1 plus sine x. And then our second fraction, we're going to multiply our numerator and denominator by 1 minus sine x. So then we get 1 minus sine x over 1 plus sine x times 1 minus sine x. So now that we have a common denominator, we can go ahead and combine this into one fraction. Now our numerator is going to be 1 plus sine x. Distributing the minus sign is going to give us minus 1 plus sine x. And then, like I said earlier, the denominator is going to be 1 minus sine squared x because we have a difference of squares here. So now the numerator, the 1's going to cancel out, and we're left with 2 sine x. And then the denominator, we can use our Pythagorean identity, which says that sine squared x plus cos squared x is equal to 1. And if we were to isolate cos squared x, we get 1 minus sine squared x is equal to cos squared x. So we can go ahead and replace our denominator. And now we just need to use our quotient identity, and this is equal to 2 times. So one of them is going to be sine x over cos x, which is just tangent x. And then we have an additional cos x in the denominator. So 1 over cos x, that would just be secant x. And that is exactly what we have on the right-hand side. So this is where we would stop. Now for our second problem, we have something that looks complicated on the left side and the right side. At first glance, we can see that our numerator and our denominator are conjugates of each other. So we might be tempted to multiply the top and bottom by, say, cos x minus sine x. But that's not going to get us any closer to the right-hand side. But upon closer inspection, we can see that both sides have the same format. We have a fraction on each side, and then we have a term minus a term on top, and a term plus a term on the bottom. So let's go ahead and try to take the right-hand side and convert everything in terms of sine and cosine first to see what happens. So we would start with 1 minus tangent x over 1 plus tan x. So we're going to use our quotient identity, and this is going to be 1 minus sine x over cos x. And then our denominator is going to be 1 plus sine x over cos x. And now we're going to go ahead and put everything over cos x. So then our numerator is now going to be cos x minus sine x over cosine x. And then our denominator is going to be cos x plus sine x over cosine x. And since we have over cos x in both the numerator and the denominator, we can go ahead and cancel that out. And that means we're left with cos x minus sine x on top. And then our denominator is going to be cos x plus sine x. And in fact, that's actually exactly what we have on the left-hand side. So by changing our tangent x to in terms of sine x and cos x, we've actually gone ahead and proved this identity. So this question shows us that sometimes we don't need to jump straight into using all these other fancy identities that we've learned. Sometimes just changing everything to sine and cosine is enough. Now for our third problem, we can see that we have a cos 2x. So usually when we see a double angle, that tells us we should use our double angle identity. Now again, cos 2x is the one that has 3 different identities for us to choose from. But we can see that eventually we want to end up with just a single term on the right-hand side. And the fact that we have a 1 in the front right now is going to prevent that. So we want to pick the identity that's going to help us get rid of this 1. And the one that does that is going to be cos 2x is equal to 1 minus 2 times sine squared x. And the reason is because we're going to have 1 minus that, and then the 1's going to cancel. So let's go ahead and use the identity and see what happens. So we start with 1 minus cos 2x over sine x. And this is going to be equal to 1 minus, and then in bracket, we're going to have 1 minus 2 sine squared x. And this is still over sine x. So like what we said earlier, the 1 is now going to cancel. So then we have 1 minus 1, and then minus 2 sine squared x. So that becomes positive 2 sine squared x over sine x. And now one of the sine x is going to cancel from the top and bottom, which means we're left with just 2 sine x. And that's exactly what we have on the right-hand side. And now we have arrived at the last problem of this video. And this one is going to take a little bit more thinking. So first, we see that on the left-hand side, we have a sine 2x. So naturally, we're going to see if we can use our double angle identity here. So let's take a look at what happens. If we use our double angle identity, we're going to get sine x plus sine 2x. So the first term stays, that'll just be sine x. And then sine 2x is 2 times sine x cos x. And now, even though, yes, we can factor out a sine x, there's no way for us to get to the right-hand side. In fact, if you look at the right-hand side, we have 2 different angles. We have a 3x over 2, and then we have an x over 2. And there's no way for us to get that using the double angle identity. So that means this way is not going to work. So the fact that we actually have 2 different angles here tells us that double angle identity is not going to work, because double angle means that we have 2 of the same angle. So because they're different, that kind of gives us a hint that maybe we should be using our sum and difference identity. Now the sum and difference identity that gives us sine of an angle multiplied by cosine of an angle is the sum and difference identity involving sine. So let's go ahead and write that down. So we're going to have sine of, and the 2 angles that we have are going to be 3x over 2 and x over 2. So if we were to add them together, this is going to give us sine of the first angle multiplied by cosine of the second angle plus cosine of the first angle multiplied by sine of the second angle. So now comparing this to what we have, we can see that this part is what we want because that's right here. But we have this extra part that we don't want. So this is what happens if we add these 2 angles together. But we can see that if we were to subtract them, then this sign is going to turn into a minus. So let's go ahead and write that one down as well. So we'll write this as our first one, and then the second one is going to be sine of 3x over 2 minus x over 2. Now this is going to be sine of the first angle multiplied by cosine of the second angle. And now we subtract cosine of the first angle multiplied by sine of the second angle. So remember how earlier we said that we didn't want this part because it's not on the right-hand side. Well, this is now perfect because for our second expression, we now have minus the exact same thing. So now what we're going to do is we're going to take our first equation and we're going to add it to our second equation. So that means on the left-hand side, we would have sine of 3x over 2 plus x over 2 plus sine of 3x over 2 minus x over 2. And then now the right-hand side, the second part of the expression is going to cancel out. And then the first part, well, that part is identical. So if we add them, we basically get two of them. So that will be 2 times sine of 3x over 2 times cosine of x over 2. And now this is perfect because this is exactly what we have on the right-hand side of the identity. So meaning we get 2 times sine of 3x over 2 times cosine of x over 2 is equal to this part right here. But notice how we can actually add these two angles because 3x over 2 plus x over 2 is just 4x over 2. So then this is equal to sine of 4x over 2, which is just 2x. And then the second term is going to be sine of, that'll be 2x over 2, which is just x. And that is now what we have right over here. So thus, we have now proven this identity. And now let's do a quick recap of what we covered in this video. So some of the strategies that we covered in this video are rewriting things in terms of sine and cosine, and spotting Pythagorean identities hidden behind conjugates, and when to use the double angle identity versus when to use our sum and difference identity. Proving identities is about making strategic choices. You're not just randomly guessing what the next step should be. You're manipulating the expressions by looking at what your end result should be, and by identifying algebraic patterns that can help you get there. And now it is your turn to give this a try. Can you prove the identity on the screen here? And just a warning, this one is a tough one. So if you figure this one out, make sure to leave your answer in the comments below. And let us know if you'd like to see more content on proving trig identities in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.